Okay, welcome students. So in this video, we're going to start chapter 2 today. We're going to talk about nuclear chemistry. So when you hear nuclear chemistry, it brings to mind some things for me anyway. I went online and I got some different pictures off of just Google Images. And here's what I found when you type in nuclear chemistry. You find some picture like this. Guys, why would this be included in nuclear chemistry? What is this part of the atom right there? That's the nucleus. Okay, that's what we're talking about. That's the part of the atom that we're going to be focusing on in this chapter. Okay, so what particles are found in the nucleus? Protons and what else? Okay, we're going to be really looking at these two particles, the protons and the neutrons. We'll save electrons for the rest of the year. We'll talk about electrons a lot, but just not in this chapter. Okay, what is this a symbol of? Radiation. Yeah, that's like the symbol for radiation. If there's radiation around, you'll usually see something like that. Okay, radiation comes from the nucleus of an atom. And so that's why I've got a picture of that. What is this a picture of? That's a nuclear power plant, yeah. Everyone thinks these are the really cool parts of the nuclear power plant, but actually what's the cool part is happening in this little domed building. Okay? That's where the nuclear reactions are taking place, well below ground and under and in the water. And then it heats up the water, and why do they want to heat up the water?
So it produces steam.
Yeah, that steam that comes up turns the turbine, and the turbine produces the electrical power. Same thing at IPP, right?
Yeah.
How is IPP different than this nuclear power plant?
They use coal.
Good. They use coal to heat the water. From that point on, it's just like this one. This one uses nuclear reactions to heat the water. And we'll talk about what reaction that is later. Also, you had to throw in a picture like this, right? What is this?
Nuclear bomb.
Yeah, a nuclear bomb has just been detonated. You see that mushroom cloud? That's kind of a giveaway. And so nuclear weapons should come to mind. We'll talk about nuclear weapons, how they work. It's kind of cool. But it all starts from the nucleus of the atom. So that's what we're going to study in this chapter. Cool stuff. All right, so hopefully you're following along in your guided notes. Chapter 2 guided notes. Here we go. So there's two forces that hold an atom together. Two forces. We learned a little bit about this first force last chapter. This is called the electromagnetic force. The electromagnetic force keeps electrons near the nucleus. How does it do that? Well, electrons are negative, and in the nucleus there's protons, which are positive. Is there an attraction there, guys? Or do they repel? Opposites do what? Attract. So that's what the electromagnetic force is this force of attraction between oppositely charged particles. That's what's holding these electrons near the nucleus. Otherwise, they'd just be free to fly off. Okay, so that's one force that's holding the atom together, the electrons near the nucleus. But the other force is the force that we're going to study in this chapter. It's called the nuclear force. Okay? The nuclear force keeps the nucleus from breaking apart. It keeps the nucleus from breaking apart. So let's look at the nucleus, guys. Look at this part of the atom right here. Nobody's asked me this question yet, but what do you notice? In terms of the electromagnetic force, what should happen with the nucleus? It should what? It should fall apart. It should be like a pushing away from each other, right? What's in the nucleus? What are these plus signs here? These are protons. And what are these guys? Neutrons. Well, they don't have a charge. They're neutral. But what if you got a bunch of protons together? What should happen, guys? They should push each other away, right? They should repel each other. And that's exactly what happens. So there needs to be a force in order to overcome that electromagnetic force that pushes them apart. And that force is called the nuclear force. Okay, so what is the nuclear force? Well, we just talked about this. The electromagnetic force should cause the nucleus to break apart. If you have a bunch of these protons sitting next to each other, do protons like other protons? No, they want to push away from each other. Positive charge, like charges repel, so they want to break apart. But it doesn't break apart. But it doesn't. And that's because of the strong force. The strong force, a lot of people call it either the strong force or the nuclear force. Same thing. Or the strong nuclear force, if you want to combine those two terms. The nuclear force overcomes the electromagnetic forces as long as the protons are very close together. So as long as they're close together, this works. And that seems a little bit counterintuitive, doesn't it? Because you would think if you got them closer together, they would push each other, push away even stronger. But as long as they're very close together, this nuclear force works. Here's the analogy that I use. You've all made or maybe seen, a rubber band ball, right? So you start it with a couple of rubber bands, you kind of put them around each other, and you keep going, and it gets bigger and bigger and bigger, right? And the rubber bands kind of hold the ball together. But what happens if that ball gets too big, and you're using the same size of rubber bands? Eventually, are you going to reach a point at which these rubber bands break? Right? And that's exactly what happens with the nucleus. If the nucleus becomes too large, the nuclear force is not strong enough to hold it together anymore. And the nucleus falls apart. So think of it like the nuclear force is like a rubber band ball. As long as it's small, the nucleus is small, you're good. It's going to stay together. But if it gets too large, they break apart. Now I want to show you on the periodic table. So if you're watching the video, hopefully you have a periodic table out. I want you to look up here. How many protons does uranium have? 92. That's a lot of protons, right? Well, notice what happens after you get past 92. Did you notice how it went from black to white? At about 92 protons, that's about the point where things start to get too big in the nucleus. There's too many protons in this nucleus for it to be stable anymore. It can't hold the nucleus together, and so it starts breaking apart and becomes radioactive. And so that's what the white background on this periodic table tells us, is that NP would have isotopes that are all radioactive. Okay, questions?
What about technique?
Okay, you'll notice number 43, Tc. It's just a weird element. All of its isotopes are radioactive. We'll talk about that later. But yeah, usually you have to get above 92 other than 43. Yeah?
What about PM?
What about what?
PM.
61. Okay, 61. Same story. Same story. So the white background here tells you guys that all of the isotopes of this element are radioactive, which means that their nucleus breaks apart. All right, good questions. We'll talk about how it breaks apart and why it does that in just a second. Okay, there's this thing called the nuclear strong force. It holds the nucleus together. We've talked about that. The nuclear force is 100 times stronger than the electromagnetic force. So it's a very, very strong force. It's 100 times stronger than the electromagnetic force. And it acts like a glue to hold that nucleus together. So even though the protons want to repel because of the electromagnetic force, that nuclear force is 100 times stronger. So it's not going to let those protons push each other apart. That nucleus is still going to be stable as long as it's not too big. Okay, so what determines if a nucleus will be radioactive? That's a good question. What determines that? Here's the answer, okay? The neutron to proton ratio in the nucleus is an important part of stability. So we're going to look at the number of neutrons and the number of protons. And we're going to compare those two into a ratio. A ratio, guys, you remember from math class, you can have a ratio of 4 to 8, or maybe 5 to 3, That's a ratio. It's just a comparison of two numbers. What we're going to be comparing is neutrons to protons found in the nucleus. Okay, for small, stable atoms, you will see one neutron for every one proton. So what's the neutron to proton ratio here? If you have one neutron for every proton? 1 to 1. That's a 1 to 1 ratio. Now, if you're a small element, a small atom, and you're stable, you're going to have a 1 to 1 neutron to proton ratio. Okay. For example, let's go to helium. If you look at helium on the periodic table, what's its atomic number? 2. What's its mass number? 4. So how many neutrons? 2. 2 to 2. Is that a 1 to 1 ratio?
Yeah.
Yeah. 2 to 2. Can that be reduced? Yeah, that's 1 to 1. So helium is a very stable element. It is not radioactive. It's not going to break apart. Okay, let's look at bigger ones though. Now, if you're bigger, you can still be stable. You can still be a stable atom, but you've got to increase your neutron to proton ratio to 1.5 to 1. 1.5 neutrons for every one proton. We haven't really talked about neutrons. We know they have a charge of 0 and a mass of 1, but that's about all we know. Neutrons, why are they there? They aid to increase the nuclear force in larger atoms. So the more neutrons you put in between those protons, the better in larger atoms. It helps space them out just a little bit more. Okay? So neutrons aid to increase the nuclear force in larger atoms. Okay, in this final bullet here on this page, it says the nucleus with 82 protons or more will be radioactive regardless of how many neutrons it has because of proton repulsion. Okay? So above 82, 82 is lead, guys, Pb. So once you get beyond 82, you're going to start seeing some radioactive isotopes. Okay, this is 82 is lead, Pb. So lead is our last really stable element on the periodic table. You get larger than that, there's just so many protons that it's not going to be stable in the nucleus. So, okay, we're going to spend a lot of time covering this graph right here. This is an important graph. This is called the band of stability graph. It's used a lot in nuclear chemistry. If you look at it, and this is what you should do with all graphs, is look at the axes. What is the y-axis labeled? Number of neutrons. What's the x-axis labeled? Number of protons. So all we're going to do is find out how many neutrons it has. Maybe it has 90. Okay? 90 neutrons. And we're going to make a mark. Let's say it has 60, a little more than 60 protons, and we plot it right there. So we just make a plot. Where it lies on this blue space right here, this is called the band of stability. So I'm going to outline it. Okay, this whole blob right here is called the band of stability. Now, where your plot, your point lies on this band of stability will tell a nuclear chemist a lot. It tells you whether it's stable, whether it's radioactive, or whether it really wouldn't exist in nature. It's just too unstable to even really form. Okay? Okay, so it says to plot carbon-12, lead-207, and uranium-238. So let's do that. Let's do it for carbon-12. How many protons? Carbon. 6. So protons down here, this would be 10, so 6 about right here, somewhere. Okay, I'll make a mark. Okay, how many neutrons would carbon-12 have? 6. So again, just a little bit below there. We plot it. Maybe right there. Okay, so is it on that band of stability? Yeah. So it's on the band of stability. And so you would keep doing that for lead-207. We could do it for lead-207 or uranium-238. And that's what we're going to do in the coming slides. All right. So graph the number of protons on the x-axis and the number of neutrons on the y-axis. Now, if your point is in the middle of the band of stability, so let's say you plotted it and it lies right in the middle of the band of stability. What does that mean? Well, that means that the atom is stable and it's not radioactive. So that nucleus is very stable. So if you're right in the middle, like for example this yellow dot right here, right in the middle, potassium 41, that atom is stable. It's not going to be radioactive. Okay? So if it's in the middle, it's stable. But what if it's on the edge of the band of stability? So now you're on the edge of this band of stability. What does that mean? That means the nucleus is going to be unstable and it's going to be radioactive. Okay? An unstable nuclei produces radioactivity, so we say that it's radioactive. All right, so let's talk about the third condition. What if you plot it? What if you plot your point and it's completely off the band of stability, like this turquoise dot right here? What would that mean?
It's never existed.
Good. It means the atom it doesn't exist in nature because it's too unstable. If it formed, it would just break apart in milliseconds. Okay? So if it's completely off the band of stability, it's too unstable to exist in nature. It does not exist in nature. So let me ask you a question. Stable or unstable?
Stable.
Stable. Does this one give off radiation? No. Stable or unstable? Unstable. Does it give off radiation?
Yes.
Yes. Could you find this isotope in nature? Yeah, it's stable enough to form, but it is radioactive. What about this one?
Not enough to form.
Could you find this one in nature?
No.
No. If it did form, it would break apart really fast. Does this give off radiation though?
Yes.
Yes. Yeah. So it'd be radioactive. Okay. Okay, we're going to pause the video here. We've learned enough to do a worksheet in your student workbook. So if you guys would turn to the worksheet, it says Band of Stability Worksheet. Okay? So I'm going to pause the video while you complete that worksheet. Okay, so hopefully that gives you a good idea about how to determine if an atom is stable or unstable, whether it gives off radiation or whether it does not give off radiation. So, just before we move on, what if you plot it and it's on the edge of the band of stability? Say it was right there, guys. Stable or unstable? Unstable. But would it exist in nature? Yes. Would it give off radiation? Yes. What about right here? Stable or unstable? Stable. Would it give off radiation? No. What about right here? Would you ever find one in nature? No. How come?
It would fall apart.
Yeah, it's too unstable. The protons pushing apart too strongly would fall apart. So yes, it would give off radiation, but it would not be found in nature because it would decompose really quickly. Okay, let's continue on. We're going to talk about the different kinds of radioactive decay. First of all, let's talk about radioactive decay for a second. What does decay mean? What does it mean for something to decay?
It breaks down.
It breaks down, yeah. When something dies, will it break down and decay?
Yeah.
Sure. Well, all we're talking about with radioactive decay is how a nucleus will break down and what it breaks down into. So what we start with and what we end with, really. Okay, an unstable nucleus will emit particles of alpha, beta, or gamma rays, aka radiation, to become a more stable element. So if it's not stable, it's going to give off this radiation in order to become a more stable element. But it talked about three kinds of radiation. What are the three kinds of radiation? Alpha, there's alpha particles, there's beta particles, and then there's this energy, which is called gamma rays. It's not a particle, but it's just it's energy, so we call it a gamma ray. Okay, so why would they do that? Why would they give off radiation? To become more stable. So if you look at uranium right here, and let's say it gives off, it goes through some changes in the nucleus, because it's so unstable, it's going to give off these radioactive particles, either alpha, beta, and gamma rays. And who does it become? Lead. Is lead stable? Yeah. Lead is stable. And so if it's unstable, it's going to give off radiation until it becomes stable. What do you notice about the size of uranium compared to the size of lead? So uranium is 92, lead is 82.
It's smaller.
Yeah, it's smaller. So by giving off these radioactive particles, the nucleus becomes smaller until it's stable enough to not be radioactive. Okay, this happens naturally and spontaneously. You can't predict exactly when it's going to happen, but it happens naturally and spontaneously. The proton to neutron ratio determines stability. We just talked about that, the band of stability. So this proton to neutron ratio, we talked about the band of stability graph. Elements with an atomic number of 82 or higher are radioactive, no matter how many neutrons they have. The nuclear force only works when protons are very close, and so the nucleus is smaller. So after lead, there are going to be radioactive isotopes. Okay, there's three types of radiation that can be given off from an unstable nucleus. So there's three types of particles that can be emitted from an unstable nucleus. Emitted just means given off. So it gives off these radioactive particles. Number one is alpha particles. Alpha is given this symbol. It's kind of a funny looking A, a fancy A. It's a Greek letter, alpha. And that's how you'd write it as a Greek letter. So there's alpha particles, there's beta particles, and beta is a Greek letter. We write it kind of like a fancy B. And then there's this energy. It's not a particle at all, it's just an energy ray. It's kind of written as a backwards Y, sort of. A backwards Y. But a lot of chemistry textbooks will also write it as a lowercase g. So please make that note as well. If you see a backwards y or a lowercase g, it means gamma rays. Okay, we're going to break down each one of these three types of radiation and talk about them in a little bit more detail. You can see it on this slide. We're going to talk about them in more detail in the coming slides. But an alpha particle is really just a helium-4 nucleus. There's 2 protons and 2 neutrons. A beta particle is really just an electron. And the gamma ray is really just a photon, which means light, electromagnetic radiation, energy. Okay, let's talk about the alpha particle first. The symbol for an alpha particle is 4,2He. So 4 is the mass number, 2 is the atomic number, and He is the symbol. It's really just a helium nucleus. The 2 protons and 2 neutrons. So on the test, if I ask you what an alpha particle is, hopefully you will say it's 2 protons and 2 neutrons. That's what's given off if an element gives off alpha. It gives off an alpha particle. Okay, the problem. Why would this is what the problem would be if this element needed to give off an alpha particle. The nucleus has too many protons, which causes excessive repulsion. So down here, this element, Pu-240, must have too many protons. So what's it going to do to solve that? The solution is, in an attempt to reduce the repulsion between protons, a helium nucleus is emitted. So it's going to throw out an alpha particle. How many protons did it lose, guys? 2. How many neutrons did it lose? 2. It lost 2 protons and 2 neutrons. Did it lose a lot of mass? Yeah, how much did the mass go down by?
4.
4. Because each one of these has an atomic mass unit of 1. So it lost 4 AMU. It's getting smaller, right? So what can you say about Pu-240 and uranium-236? Which one's more stable? Which one's more stable? This one's more stable. Yeah, that's the problem. If this was unstable, it gives off an alpha particle to become a more stable element. Okay. The charge of an alpha particle is positive. Why is it positive?
No electrons.
There's no electrons. How many protons do you have? 2. How many neutrons? 2. So it's really plus 2. For each particle, its charge is plus 2. Okay, let's go to beta decay. Let's talk about a beta particle here. A symbol for a beta particle is this. You have 0 as the mass number, a -1 for the atomic number, and this E. Why is it an E? Because really a beta particle is just an electron. So that E means electron. So why would an element give off a beta particle? Here's the problem. It has too many neutrons, which causes instability. So remember, alpha particle was given off because there was too many protons. Now if an atom has too many neutrons, it will give off a beta particle. The solution, so why does it give off, or how does it solve that problem? A neutron, this is kind of crazy here, let's pay attention. So a neutron is split into a proton and an electron. What? It takes a neutron and does what to it? It splits a neutron into what? Into a proton and an electron. Okay? Well, what happens with that electron? The electron is then emitted at high speeds. So the electron is then emitted, which means given off at high speeds. Okay? So a beta particle is really just an electron that's left the nucleus at high speeds. Okay, kind of a little bit crazy there with the beta particle, but that's what it is. Okay, the proton, however, is kept. So remember that neutron was converted into an electron and a proton. The electron gets shot off, the proton is kept. So let's look at that now that we know. So this is Ra-228. How many protons did it have? 88. It became Ac-228. How many protons did it have? 89. So what happened here? It got bigger in terms of the number of
Can I go to the bathroom?
protons. So yeah, you added a proton, but what happened to the neutrons? Okay? Can somebody tell me how many neutrons would be found right here? You take 228 and minus 88. What do you get? What is it?
140.
140. Okay? That one had 140. How many neutrons over here?
139.
139. So what happened to the number of neutrons, guys? It got smaller. That's why these atoms would give off a beta particle to get rid of neutrons. So if you got too many neutrons, it gives off a beta particle. What is this really? It's really just a what? An electron. Okay. So beta particles are kind of crazy. Oh, what's the charge of a beta particle? If it's an electron? Negative. It's minus 1 charge.
What's an alpha?
The charge of an alpha, that was positive. Yeah, plus 2. Okay, we've got one more to look at, and that's gamma, a gamma ray. So the symbol for a gamma ray is given right here. Symbol for a gamma ray is 0 for the mass number, 0 for the atomic number, with a Y. I also want you to write this. Some chemistry textbooks will write it like this, 0, 0, G. So if you see that, that's the same thing. And some will write with a lowercase, little backwards Y sort of thing, like that. So anyway, those are the symbols for a gamma ray. So I want you to remember that gamma rays have very high energy. These are the ones that do the most damage. They have a lot of energy. The problem, why would an atom give off gamma radiation? Well, the nucleus is at too high of energy. So if that nucleus just has too much energy, it's going to give off a gamma ray and lose some of that energy. The solution, the nucleus falls down to a lower energy state, and in the process emits a high energy photon known as a gamma ray or a gamma particle. So let's look over here. It was Pu 240. Now what is it? Pu 240. Did it change? Didn't change at all. The atomic number was 94, now it's still 94. But what's different? Why is there a little star here? What do you think that star means? This one's high energy. This nucleus just has a lot of energy. So to solve that problem, it shoots off this gamma ray, loses some of that energy, but in the process it still stays the same. Okay. The charge. What do you think the charge is? Neutral. Look, we got 0 protons here and 0 neutrons. It's neutral. Oh, and also, usually you will see a gamma ray given off whenever there is alpha and beta radiation. So if you see alpha or beta, most of the time you'll see gamma at the same time. Okay, this is an important slide. I want you to take a look at it for a sec. It's not in the guided notes, but maybe I should have put it in there. Anyway, if this is a radioactive source right here, it's giving off alpha, beta, and gamma rays. Which one goes straight through this and goes through, straight through? Even if you put a positive side of the magnet here and a negative side of the magnet here, which one's going to be unaffected by the magnetic charge? That's gamma. Why is gamma not affected? It doesn't have a charge. It doesn't care that there's positive and negative charges introduced right there. Which one's going to be attracted to the positive side of the magnet? The beta, because it is negatively charged. The beta is really an electron. Remember how we talked about the cathode ray tube experiment? The electrons got attracted to the positive side of the magnet. Well, beta particles, because they are electrons, same thing. Which one's attracted to the negative side of the magnet? Alpha particles, because they have a positive charge. Okay. So, test question, a possible test question, Keaton. Alpha, beta, or gamma is attracted to a negative charge. Which one would be attracted to the negative side of a magnet? Alpha, because it is +2. Remember, opposites attract. Okay. Okay, penetrating power. This is quite important. We're going to spend some time here. An alpha particle. These particles can be stopped by a piece of paper. You hold up a piece of paper and it's going to stop it. Okay? So are they very dangerous? No. Would your clothes stop it? Yeah. So, I mean, they're the least dangerous of the three. The least dangerous. Okay? Beta particles can be stopped by, let's just call it a piece of sheet metal. Even a thin piece of sheet metal is going to stop a beta particle. It can be stopped by clothing, wood, or aluminum. Also, when inhaled or ingested, they can be very dangerous. So you think about it, you're inhaling them into your lungs. It can still go through thin stuff. You know. So they're, in the terms of penetrating power, they're the middle. Okay, now the most dangerous, or the most penetrating, are the gamma rays. These particles are highly penetrating, can be stopped by a thick concrete or lead. They will penetrate deep into your body and alter DNA. These are the ones that go in and break your DNA and cause mutations and can lead to cancer. So gamma rays are the most dangerous because they penetrate the farthest. go right through your body and break DNA. Okay. Let's talk about the reason for the penetrating power. Why is it the way it is? Why do you think alpha particles are stopped by a piece of paper, guys? Why do you think these are stopped by a piece of paper? These have a large mass. They're just more massive. It's easier for things to stop an alpha particle. They're more massive. It's got 2 protons and 2 neutrons. Okay, let's look at a beta. What is a beta particle, really? What is it? It's really just an electron. Are they as massive as the alpha? No, they're much smaller, so they're able to go through farther. Okay, so they have less mass. Now the gamma ray, does it even have mass at all? No mass. These things don't have any mass. It's just an energy ray that can penetrate even many feet of concrete. So because there's just really nothing to them, they can go through a lot. Okay, there's a summary of the 3 types of radiation in your guided notes. I'd like you to take a second and fill that out. This is the stuff that I would expect you to remember and to know. This is what I will test you on. This is what's on this table. Okay, so I think we're going to stop the video at this point, and we'll continue on talking about this in the next video. Hopefully that helped.